Okay. So this was the quiz. So the first question was to give all the three-dimensional representations of S3 cross Z mod 60 up to isomorphism. Yeah. So of course, if you are given a representation, so this is just using the fact that every representation you can decompose into the sum of irreducible representation, and then count all the irreducible representation of S3 cross Z mod 60. Yeah, and combine these two. So if you are given a representation, so V is so this is for 1. V is a representation of S3 any group for that matter, but in this case Z mod 60. Then you can write it as V as direct sum of irreducible representation. Yeah, V1 direct sum, V2, and so on. Vi is irreducible. So if you want to count all three-dimensional representation, then it has to be either, I mean, so there can be only at most three components, and then we count all the irreducible representations of various dimensions. Yeah, so there could be three irreducible representation of dimension 1, or there could be one irreducible representation of dimension 3, or one irreducible representation of dimension 2, and one of dimension 1. Yeah. So let's just count the number of irreducible representations of S3, and then it's a combinatorial problem. S3 cross Z mod 60, and then it's a combinatorial problem. And we know what the irreducible representations of S3 and cross Z mod 60 look like. Yeah. So any irreducible representation of S3 cross Z mod 60 is basically an irreducible representation of S3 and a tensor irreducible representation of Z mod 60. So Z mod 60 we know. So how many irreducible representations Z mod 60 has? 6, yeah, and they all corresponds to various group homomorphisms from Z mod 60 to C star. Yeah, so maybe so theta. So there are 6. Yeah, so maybe I'll not write it down, all the representation. So there are 6, 1, and all of them are one-dimensional. 6 one-dimensional. So we don't, I mean, one can actually compute these, all these representation, but I don't want to, we don't need to compute it. We just have to count how many are there. One-dimensional representations of Z mod 60. Yeah. Corresponding to each corresponding to a homomorphism from Z mod 60 to C star. And there are 6 of them. You send 1 to the 6th root of unities, yeah, and it determines the homomorphism. And for S3, there are so for S3, there are how many irreducible representations? So we saw this in class, yeah. So for S3, there are 2 one-dimensional representation. So one is the trivial one, and the other one is the sign one. Yeah. So the permutation sigma going to sine of sigma, and then we saw that there has to be one more irreducible representation, and it has to be of dimension 2. Yeah, and one two-dimensional representation. So we don't really need to know what Yeah, though we computed it. Yeah, we figured out what the irreducible representations of S3 are. So by the results we have seen, the product has so S3 plus Z mod 6C has so the irreducible representations are, you take a irreducible representation of Z mod 6C and a irreducible representation of S3 and tensor it. Yeah, as so there are 6 one-dimensional representations. So there will be 12 one-dimensional irreducible representations. So you tensor each of these representations of S3 with these one-dimensional representations of Z mod 6C. So you'll get 12 one-dimensional representation and 6 two-dimensional irreducible representations. So unfortunately, I haven't looked at your answer script, so I'm not sure how many of you have got all of this, but anyway. So you get that there are 12 one-dimensional representation and 6 two-dimensional representation. Now you want to make up the dimension 3. So there are 2 ways of doing it. One is that all of them are 3-dimensional, one-dimensional representation. So there are 3. So you take direct sum of 3 one-dimensional representation. And the other way is that it has to have at 1 two-dimensional representation and 1 one-dimensional. These are the only ways. Yeah, you can't have 2 two-dimensional representation. Then it will become 4. Yeah. So the number is 12 choose 3. So number of 3-dimensional representations of let me just change some setting here. Okay. So the number of 3-dimensional representations of S3 cross Z mod 6C is so if you consider sum of all one-dimensional representation making a 3-dimensional representation, there are 12 choose 3 ways of doing it. So you have to choose 3 of the one-dimensional representation and take a sum. Yeah. So we are trying to do up to isomorphism. So you can, I mean, if you add it in different order, it will give you isomorphic. Yeah? And the other way is to choose 1 two-dimensional and 1 one-dimensional. Yeah, so that is 6 choose 1.
Sir?
Yes?
There can be 2 like same components also, right?
Yeah, so this will miss the cases where you take one-dimensional representation and direct sum it 3 times with itself.
Yeah. So I have to add more things, yeah? So, yeah, so that's it. So 6 choose 1 and 12 choose 1, and then you have to add more, yeah? So, yeah, so another is that a one-dimensional representation appears with multiplicity 2, and one-dimensional representation appears with multiplicity 3. Yeah, so maybe add those 2 as well. So that is let's say 12 choose 1 times 12 choose 1. So that is so you are taking one-dimensional representation with multiplicity 2, multiplicity 2, you are choosing it, so that is choosing one of them, and then sorry, so this is not the right way to do it. So you do 12 choose 2, yeah, and counting arguments, I forgot. So you have to do 12 choose 2, that you can make it by choosing two representations. Yeah, 12 choose 2, and one of them will have to be with multiplicity 2, and the other one has to be with multiplicity 1. Yeah. So I think, yeah, this counts everything. Yeah.
So this has to be twice because like the order matters over here. One is with 2, one is with 1.
Yes, yeah, you're right. Yeah. So
There is one case with all three.
you have to take ordered pair. Yeah. So 12 choose. So 2 times 12 choose 2, and then the last one is you choose one of them and with multiplicity 3. Yeah. So these will add up all you take the sum of these, and this will give you all the three-dimensional representations of S3 plus Z mod 60. Yeah. So whatever this number is. Yeah. So what is the answer? If someone knows, remembers?
436.
436. Okay. Okay, so this is how you can, so the representation theory part ends more or less here, yeah, and then this is more or less combinatorial part. The remaining is combinatorial. Now, for the second one, can I rate it? Yeah, I can rate it. Okay, so for the second one, here you'll have to use some character theory, yeah, but not too complicated. So you have given a finite group G, and V is a regular representation. V is the regular representation, so V is Kg. Yeah, and the objective is to compute the multiplicities of every irreducible representation of V tensor. Yeah. So V tensor V dual. Yeah. So V tensor V dual is some representation of G, and of course V you can decompose it as a certain number of irreducible representation. Yeah. So you can maybe write it as dx sum of Vi per freezing. Dx sum of Vi per Ni, I equals 1 to M. So there, so Vi irreducible key representation of degree Ni. Degree means the dimension of Vi. So we know that V looks like this. Yeah, so V tensor V. So the objective here is to write this as the sum of I equals 1 to M Vi per Ri. And so we know that it is going to be of this form for some Ri. For some Ri is greater or equal to 0. Yeah. So the objective is to compute Ri. Compute Ri. Right. So we know how. So if you remember how we computed these. So in regular representation, how we did this. So we used characters. So that is what you have to do here as well. Yeah. So character of V, we know is for regular representation, it is for identity, it is size of G, and phi V G is 0, G not for G not equal to the identity. Yeah. And then we figured out this is Ni by taking the inner product. Yeah. So in fact, Ri we know is so maybe first let's just recall. So note that Ni is just chi V comma chi Vi by this orthogonality of characters. Yeah? Chi V you can write it as sum of chi V Ni times chi Vi, and then Ni you get it by inner product. but this and then you realize Ni has to be this because this is just the dimension of Vi. So it is size of so the formula for this, if you get this is dimension of Vi. So finally, to get Ri, you will use the same trick. So so first you have to compute the character of Vi tensor Vi dual. Yeah. So we know what character of Vi tensor Vi dual is. It's character of Vi. Character of Vi times evaluated at G is character of Vi G times character of not Vi tensor, V tensor V dual. That is what we are trying to compute. So no Vi needed. So V G bar, yeah, but V and character of regular representation is a real valued function, in fact an integer valued function. So it is so this is we know what it's going to be. So for 1 it is size of G square. So this is size of G square if G is 1, 0 otherwise. So in fact, V and V dual are the same representation because they have the same character, right? So you could just as well work with V tensor V, but it doesn't matter. All we care is what the character is. Now, Ri, as we know, is going to be V tensor V dual. I think our notation was a line here. So let's put a line, character of Vi. And this, remember the formula is 1 over G summation G in G, chi V tensor V dual G, chi bar Vi G. Yeah, so this is the formula. But the point is, as in the regular representation, except for one value, the rest of the values of the characters are 0. Yeah, so this is 1 over size of G, and for G equals 1, you have value size of G whole square, and this has value Ni. Yeah. So what you get is size of G times Ni. Yeah. So the multiplicity Ri is just Ni times size of G. Okay. So that is your answer. Okay. So once you realize that you have to use the same trick as in the regular representation, then this is a straightforward problem. Okay. Any questions or comments? Okay, so I suppose it wasn't too difficult, the quiz. I'll look at your answer script today or tomorrow, and Friday. If you still have some questions about your quiz, you can ask me on Friday, or you can email me. We can discuss one-on-one as well. Yeah. So anytime if you have some question you want to discuss one-on-one, you just email me and we can do a Zoom session one-on-one. Okay. Yes.
If the method in question one slightly differs, is it fine? Like if the combinatorial part as well as the character theory part, like using that abelian group thing, I wasn't able to justify that these things are not isomorphic, the tensor products at first. So I did that thing that there is a subgroup, an abelian subgroup of index 2 inside this group. And hence all the characters are of dimension 1 or 2.
Okay.
And there are 18 conjugacy classes. So there are 18 distinct irreducible representations over there.
And you got the 12 one-dimensional and 6 two-dimensional.
Yes, sir. After that, it's fine.
Okay. Yeah, sure. So I mean, if the proof is okay, then it's okay. Yeah.
Yes, sir. Thank you, sir. So, and the combinatorial method also differed a bit. Like instead of breaking it into so many parts, I just considered the number of solutions of that equation.
That's okay. I mean, combinatorial method, there are many ways of thinking about it. Yeah? No issues.
Okay, sir. Thank you, sir.
I mean, of course, you should get these numbers, 12 and 6, yeah? And then...
Yes, after that.
Yeah.
Just calculation.
Yeah, sure.
Yes.
No
Thank you, sir.
You're welcome. Any other questions or comments?
Like, what's the distribution agar if we make some mistake in the combinatorial part, how much will you get?
I won't take too many points for combinatorial, maybe 2 points or something. Yeah, so don't worry about it. Combinatorial is not the real goal of this course. Yeah, I'm sure everyone can figure out that. So I'll see. Yeah, what the breakup would be. Any other questions or comments? Okay, so maybe let's get to today's lesson then. Yeah. So so in the previous class we talked about induced representations. So what we discussed, so we defined induced representation. We saw that for every so if you are given a group G and H is a subgroup of G, so given a H representation, there is always, we also saw there is always an induced representation B containing that representation. We gave a constructive proof as well, and we gave a proof using properties. So basically, using the regular representation, you can prove the existence as well. So because regular representation of H is sort of, so regular representation of G is induced representation of regular representation of H, and then some various properties. Yeah. You can use to show that every representation of H is contained in a induced representation. So there exists an induced representation. Yeah. And we gave a explicit construction as well. Yeah. And in the homework, there will be another construction which Sarah provides as an exercise. So if you do the exercise, the homework problems, you'll see. So it's similar to this. Is instead of using, so like regular representation, remember one way to do it is write it as vector space. So you take it as direct sum of KGIs, yeah, where K is the base field. Or other ways to think of it as a set of functions from G to K. Yeah. So what Sarah does is something like that. The distinction is somewhat like that. So instead of taking direct sum of G colon H copies of W indexed by G, he takes functions from the set of left courses G mod H to W. Yeah, so W valued functions from, and then you give the operation. Okay. So anyway, so if you remember, if V is a G representation and W is a H stable subspace, we say that V is induced from W. If you can write V as a direct sum of GIWs, where GIs are where GIs are representatives of all the left cosets of H in G mod H. Yeah, so the G mod H is the set of left cosets. And So this is one way of writing it. So we wrote it. So in this in the previous part, when we defined it, we said this is rho G of W, and we saw that if G and G prime are in the same left coset, then rho G of W and rho G prime of W are same. Yeah, where rho is this. But I mean, slowly you will get tired of this rho and this theta. So from context, it is clear whether it is rho or whether it is theta. G dot W, whether it is rho, how G acts on something is clear from the context. Yeah? So that's why I've written it this way. So GIW means rho GI applied to W, which is going to be some subspace of V. And then it has to be direct sum decomposed. So these gives you, so to speak, so they are linearly disjoint. Yeah, so the intersection is 0, and that if you add them up, you get whole of V. So V is the direct sum of these guys. So now we want to relate the character of the induced representation. So we want to compute the character of V in terms of the character of W. Yeah. So I'll give you the formula today. So this is just analyzing how things happen. Yeah. So what is the character of V? So if you want to evaluate, so for G in G, character of V evaluated at G is basically by definition is trace of rho G. Yeah. And how does G act on V? So the way G acts, so we will use this decomposition. V is direct sum of GIW. There are number of pieces, yeah, where R is G colon the index of H in G. Yeah. So to compute the trace of rho G, we can what we can do is take a basis of W and G1 W, G2 W, and so on, and then think of and think of the matrix associated to rho G with respect to that basis. Yeah? So that is the philosophy you should take. Yeah. So let's see how G acts on V. Yeah. So remember the way it acts is that so on each of these pieces. So if you look at W, G will send W to the piece GW. Yeah. And what is GW? So GW has to be one of these GIW. Yeah, depending upon which left coset G belongs to. Yeah? So so this is familiar. This is similar to how we were giving this direct construction. Yeah. So G dot GI will be some so G, how will G act on GIW? So G dot GIW will be one of these GJW, yeah, and which GJ will depend upon where does G dot GI lie in, yeah. So which left coset it is, yeah. So it will be some left coset, let's say GI. So GI is going to be between 1 and R, and HI you can then determine by just taking the GJI inverse on the left, yeah. So G dot GI is GJI times HI for some GI in R and HI in H. So for I between 1 and R, we have this G times GI will be one of these. Yeah. So if W1 to Wm is a basis of W, then so GI is basically an isomorphism from W to GIW. Right? GI is actually multiplication by GI, or rho GI is actually an automorphism of V. Yeah. So of course it sends W to GIW. Yeah. So GIW1 to GIWM will be is a basis of GIW. Yeah. So I don't know if I'll use the, so I won't use the exact basis as such, but what GI does is it sends W to GIW as an isomorphism. Yeah. So this is what happens. So now if I want to compute the trace of rho G, then if I'm looking at say G1W, then G times G1W. So what will G do to G1W? It will send it to GJ1 times. So it will send it to GJ1W. Yeah. Now, if GJ1 happens to be different from G1, yeah. So if J1 is different from G1, then of course that piece will not contribute to the trace, right? So because the trace only looks at the diagonal components, yeah. So the diagonal entries of the matrices. So so I'm trying to look at how rho G acts on these individual pieces, yeah. So rho G. I'm trying to look at the action of rho G on this direct sum of GIWs, I equals 1 to R. Yeah. So on G1 it will act by sending it to G1. It will send G1W to GJ1W. Yeah. So it will send maybe G1W1 to GJ1W1, yeah, and with certain multiplicity, yeah. So or it will be so it will send G1W1 to some linear combination of GJ1W1. But if J1 is different from 1, then the G1W1, the entry. So you think of it as, yeah. So maybe I will use. So consider the consider the basis. So basis. So this is an automorphism of this guy, yeah. So let me just first complete this statement. And consider basis B to be G1W1, G1W2, and so on, G1WM, and so on, yeah. GRW1 to GRW1. So we are trying to compute the matrix with respect to this basis and then compute the trace. Yeah. So if you think about with respect to this guy, then on the first block, so you think of it as block matrices. On the first block, the trace contribution will be 0. So we only have to consider those GIs for which G times GI is same as I. Yeah. So we want to compute the trace of. Yeah, so maybe I should put it trace of, and then get to the next step. Yeah, summation I equals 1 to R. GI equals 1. GI should be equal to I. So not all I between 1 to R, but GI equals I. Trace of rho G. Restricted to GI W. Okay. So this is what. So on each piece, you look at how G acts on GIW. So if it sends GIW to something different, so GI that is GI is different from I, you forget that piece. if it sends GIW to GI itself, that is GI is equal to I, then you try to compute what the trace is. Yeah. Okay. So so you see, if G sends GI, if G sends if GI is equal to I, then G will send GIW to GIW. So this makes sense. Yeah? So, GI equals I, this implies, so if you use this identity, GI inverse, so you think about it this way, so then then G is same as GI HI GI inverse. And of course, if you act on GIW, GIW goes to W, HI preserves W, and then GI will send it back to GIW. Yeah, so this rho G restricted to GIW makes sense. It is a linear map of is an endomorphism of GIW, and so hence trace of rho G restricted to GIW makes sense. Okay. So I'm trying to divide, write down trace of rho G in terms of these block matrices. So I've ignored whatever happens in the off diagonal. I'm just looking at these diagonal pieces. Okay. So this is the first reduction. Does that make sense so far? Yeah. So I hope it makes sense. Yeah. So please ask questions if there is any doubt. Yeah. So now, once you have that, this happens. Now you just look at what is rho G. So rho G is same as GI HI GI inverse. This is what we computed. Yeah. So trace of rho G restricted to GIW is just this guy with I equals I between 1 and R, and such that GI is equal to I. Yeah. And so maybe writing GI is equal to I is better to write that so another way to think of GI is equal to I is same as saying that GI inverse GI belongs to the group H. Yeah. So it's I between 1 to R, trace of this guy. But think about it, this rho GI HI GI inverse, if you compose it with rho GI on the left, on the right, and on the left, if you compose it with rho GI inverse, this is an endomorphism of W. Yeah, because the first guy will send W to GIW, and we know that the middle guy is going to send GIW to GIW itself, and then finally rho GI inverse will send it back to W. Yeah, GIW to GW. Yeah, so it gives you an endomorphism of W. So this is an so I mean this is an endomorphism of V, but when you restrict to W, it gives you back W. Yeah. And what is this endomorphism? This is just rho HI restricted to W, but that precisely is theta HI. Yeah? So that was so remember W is the W is G stable subspace, H stable subspace of V. Yeah? So you restrict rho HI to W, and what you get is basically theta HI. Yeah? So the trace of this product of these three matrices restricted to W is same as trace of theta HI. Yeah. But then this is a conjugate, so this is same as and this implies trace of GI HI GI inverse restricted to W, same as trace of theta HI. Yeah. Because it's you just conjugate. Trace of AB is same as trace of B. You can use that with maybe this as your A and this as your B, if you like. Yeah. So you get that this is same as trace of theta hi. So now you can relate it to character of h. Yeah, because theta is a representation of h. So trace of theta hi is precisely the character of hi. And what is hi? So, since hi is GJI inverse GI, but GJI is same as GI because we are in that case. So hi is, remember, is GI inverse GI. So that tells you that instead of theta hi, you just look at the character. Trace of theta hi is same as character of the representation theta or W, evaluated as GI inverse GGI. Yeah. So now, and we are summing over the same guys. Yeah. So this is the formula. And then you can, if you want to write it without the representatives, so maybe I should just do kill. Maybe this, I wanted to box this. So 5VG, the formula is this. So maybe here I'll put, note that hi is GI inverse G. So that's what gets in this way. And now if you want to think about, you want to get rid of representatives, then what you can do is sum over all, let's say y in G. Yeah, so if you, instead of taking just certain representative GIs, you sum over all y in G. But then, of course, if you are summing for GI, so if GI has the property that GI inverse GI belongs to H, then of course GI times H will also have that property. Yeah. So if one particular representative of the coset has, then every element of that coset has. Yeah. So you are adding this H times. So all you have to do is divide by H time by H this each of these sums. Yeah. So you could do 1 over H inside, but then you can pull out. So 1 over H outside. Yeah. So that's the formula you get. Yeah. So there are two same formulas, but one is in terms of representative, the other is free of representative. Yeah. So what are you guys trying to do? So let's try to reinterpret this. So you're trying to, yeah. So you're trying to sum over y in character of y inverse GY. So you want to calculate character of the induced representation at an element G. Then you look at all the conjugates of G which lie in H. You evaluate the character, you find the character of this H at those values, and then you take the average. That is what you're doing. Yeah. So you look at all the elements G in G, which conjugates G to an element in H. You take all elements Y in G such that it conjugates G to an element in H, evaluate the character at that value and that element of H of this representation, and divide by the size of H. Okay. So this is the formula for the character, okay, of the induced representation. So yeah, so if the group is explicit, maybe you can also and you know the character, then of course you can use this formula to actually compute the induced character of the induced representation. Okay. Any questions or comments? So we will see some other properties of induced representation. Yeah, so there were some questions last time. So when induced representation is irreducible, so there is some criteria called Mackey's criteria, which is so of course so I told you that it's clear that if you start with some representation which is even if you start with an irreducible representation, then the induced representation need not be irreducible. Yeah. Now, for instance, the regular representation is also an induced representation, but it's far from irreducible. Even if you so, for instance, if you take the trivial group, right? So, so of course this is necessary. I mean, if you start with something which is not an irreducible representation, and if you induce, if you look at the induced representation, that will of course decompose. Yeah, if W is W1 plus W2, then int W is going in the GHW is going to be in the GHW1 plus in GHW2. Yeah, that we know. So it is necessary, but it's not sufficient. So there is another condition which is needed. So maybe we'll discuss that later. Yeah, it comes later in Sayre's book. So maybe we'll do that later. And then there is another thing which is called Frobenius reciprocity. Yeah. So and that is about pairing. Yeah. So we will do those two things a little later. Yeah. Maybe we should do some examples. So after the examples, maybe we'll go back to induced representation and prove these theorems. Okay, and maybe do some more calculations, work out more examples on induced representation, and then maybe end with those young Tableau and stuff, representations of SN. So that's the plan for the rest of the semester. So let's do one example today. Yeah, so there is 10 minutes. So hopefully we can discuss dihedral group, and then we'll do more examples on Friday. Okay, so let's try to so we already saw cyclic group. Yeah, so cyclic group and S3 we saw. So that's why I gave you the problem in quiz on direct sum of that. So let's try to do representations of dihedral group. So Dn. So remember, Dn is of order 2n. So the one with so I mean some people use D2n as the notation, but what it does is it's you can interpret it as symmetries of n-gon. Yeah, regular n-gon. So there are two ways to two ways to think about symmetries of n-gon. One is that you rotate it by an angle 2 pi I over n or multiples of that, and the other is to take a reflection, yeah, about the along the diagonal. So those are that's a geometric way of thinking about Dn. So it's generated by two guys. One is rotation denoted by r. R power n, and since it's of order n, R power n has to be identity, and then the reflection which we denote by S, and of course reflection has order 2, so S square must be 1. And you know, if you rotate by let's say anti-clockwise and then reflect, that is same as rotating in the other direction and then reflecting. Yeah, so that gives you this identity. So, so you can think of it that way, or you can think of it as group generated by two elements. So one of order n, the other of order 2, and R and S, and they satisfy this relation. Yeah. So elements of this are so the elements of this are r power I, or maybe I'll use I as square root of -1 here. So r power j and s times r power j between 1 and n. Yeah, so this is, so it has 2n elements. Okay, and these relations tells you how to write down the multiplication table. So there is a n gone, and so 1, 3, and so on. Yeah. So you can also think of it as a subgroup of Sn. So I suppose you know all this from group theory. Yeah, but because this is certain permutations of 1 to n, but we don't allow all permutations. We only allow permutations which will not distort the polygon, so to speak, in this n-gon. Okay, so let's try to understand the representations of Dn. Now, so Dn, of course, this has a subgroup of, so this group is of order 2n, and it has a subgroup of a cyclic subgroup of index 2, yeah, the subgroup generated by R. So that result we have seen, we know that the irreducible representations of Dn has to have degree 1 or 2. Yeah, it can't be more than 2 because it has an index 2 abelian subgroup. In fact, index 2 cyclic subgroup. So there are only two kinds of irreducible representation: one-dimensional and two-dimensional. So and one-dimensional. So there are two cases when n is even and when n is odd. So let's try to do when n is even. So one-dimensional irreducible representation, we know what they are. So they are in bijection with group homomorphisms from Dn to C star. So if you take a group homomorphism from Dn to C star, then of course S has to go to an element of order 2 because S square is 1, and R. Now, if you just look at the condition R power n equals 1, then it has to go. R has to go to an element of order n. But remember, you also have Rs is equal to SR inverse. Yeah. So I mean, so that tells you that phi Rs is phi SR inverse. Yeah. And but you know, Dn may be not a non-abelian, but C star is. Yeah, so this is phi R, phi S, or phi S, phi R, no matter which way you write it, is phi R inverse, phi S. Yeah, and you cancel it out. So what you get is phi R square is 1. Yeah. So R square has to go to 1. Yeah. So R has to go to plus or minus 1 in C star. Can't go to anything else. Yeah. So there are 4 ways of doing, and phi S square is also 1. Yeah. So R. So this phi, there are only these possibilities. R has to go to plus or so there are. So maybe I'll just write it this way. Phi, yeah, R has to be 1 or minus 1. And phi S has to be 1 or minus 1. Yeah. So these will give you all the one-dimensional represent, and all these are possible. Yeah. So if you send both R and S to be 1, so yeah, so maybe I should have a way of writing down all the representations. Yeah. So let me make a table here. R, S. So now 1, 1. So this will give you trivial. Phi 1, phi trivial, and then So that means the group homomorphism and the representation, everything is trivial. If you take R is 1 and S is -1, this does define a group homomorphism, yeah, from Dn to with here, and the kernel is going to be the cyclic group. Yeah. So that gives you some homomorphism, which is different from the trivial homomorphism. Then you can take R, the value for R is -1 and S to be 1. So that also defines group homomorphism. Yeah. And finally, -1, -1. That also defines a group. So R goes to -1 and S goes to. So all you have to check is that these relations are satisfied. Yeah. So remember, N is even, right? So if you set R to be send phi R to be -1, then phi power Rn will be 1, and S square will be 1. Phi of S square will also be 1, and phi of Rs is same as phi of R times phi of S, which is same as phi of S times phi of R inverse, because phi R and phi R inverse has the same value, right? Because phi R square is so all these possibilities are there. So and there are 4 one-dimensional representations of Dn when n is even. When n is odd, more or less the same argument tells you that basically R square has to be 1. That doesn't require n is even or odd. But if n is odd, then R square is 1. That tells you that R has to be 1. R has to go to 1 as well. Yeah, because I don't know, you just take high enough power such that so R square has to be 1, and R power some odd number has to also go to 1. Yeah, then that tells you that R has so R power n plus 1, which is an even number, will map to 1. So that tells you that R has to map. Yeah. So for one-dimensional, maybe we can just do this as well. And even, then phi R has to be 1, and phi S has to be plus or minus 1. So 1 or minus 1. So this implies 2 one-dimensional representation.
And odd.
And odd, yeah. Even we already discussed, sorry. And odd. So that's about one-dimensional representations. Now for two-dimensional representation, so we have to think about maps from Dn to linear maps of two-dimensional vector space. Yeah. So so that comes via rotations. Yeah. So you think about it. So so if I want to give so where should R go to? Yeah, GL to C. Yeah, or maybe since I'm thinking about rotation, so maybe first R. Yeah, so if I want to do it GL to R, so R should go to a rotation. Yeah, so yeah, so R has to go to a rotation, so R will go to a matrix of the form cosine. So the rotation by, so maybe I'll just write it like this: rotation by 2 pi I over n. yeah, or some multiple of this as well. But one of the representation, you can write it by saying R goes to rotation by this, and S goes to flipping. Yeah, so maybe S goes to the matrix. So flipping is this this operation. Yeah. So you interchange. So if you are thinking of real representation with representation over real vector space, you can think of it this way. But of course, once you give a map to GL and R, of course, GL and R sits in GL and C. So you can think about these representation as GLC complex representation as well. Yeah. So S has to go to this matrix. R goes to this matrix, and this defines a two-dimensional representation. This will define a two-dimensional representation of dn. Yeah, but then one has to check whether it is an irreducible representation or not. Yeah? So maybe rotation by some power of this. Some multiple of this. So let's say k is some integer. So in fact, you can take k to be between 0 and n minus 1, if you like. Yeah, so that will because after rotating by mode will be by one of these things. Yeah. So so it's almost time. So maybe I'll discuss this next time. But this matrix corresponds. So you can write it in terms of cosine theta, sine theta. But since we'll eventually consider the matrix with complex entries, if you change basis, this is that rotation matrix is actually diagonalizable. Yeah. So what you get is e power 2 pi I over n, and minus e power 2 pi I over n. Okay. So and 0, 0. Yeah. So this is where you will have to send, and I mean this or some maybe per k. Yeah. So maybe I'll do this in more detail next time. So this will give you certain representations, and then you will so we'll discuss how many two-dimensional representations. Okay. So these are all one-dimensional, but we can count how many two-dimensional representations there are going to be, because we know that these are all the number of irreducible representations are. Yeah. So there are 4 one-dimensional representation. In the even case, so maybe even case, 4 one-dimensional representation, and so some A two-dimensional representations are there. Then so summation ni squared is the order of this. Yeah. So A two-dimensional representation. So A times 4. Because 2 square is 4, 1 square is 1, should be same as 2n. Yeah. So that tells you that A has to be A plus 1 has to be n over 2. So A has to be n over 2 minus 1. Yeah. So the n over 2 minus 1 two-dimensional irreducible representations of dn, and these will give you, so they are so if you look at various guys, so k, as I said, will vary between 0 and n minus 1. Yeah, these will give you certain two-dimensional representation, and yeah, so it's counting almost by double. Yeah. So So you shouldn't, if you take the 0 guys, so you should forget about 0 as well. Yeah, so maybe 1, because 0 is not rotating, so that will correspond to some reducible representation. So you take 1 to n minus 1, yeah, then it becomes, and then rotating by 1 and rotating by n minus 1, they will lead to isomorphic representation. Yeah, so rotating by angle k and rotating by angle n minus k will give you isomorphic representation. Sending r to rotation by k and rotation by 2 pi I k over n and 2 pi I n minus k over n should give you isomorphic representation. So that will give you, tell you that there are n minus 1 over n minus 2 over 2 non-isomorphic irreducible representation. Okay, so that's roughly the whole picture. Okay, so let me stop.